Okay, so let's look at actual diode gates, real gates that we're going to build from diodes. These are the first two gates after you build your digital to binary converter. And just imagine what's going to happen here. Think about it. I'll go over the first one with you, which is the OR gate, and then you can see if you can figure out the second one, the AND gate, on your own. So imagine that we put a 5-volt input. Right. Remember, we're talking about. We're just going to pretend that these are actual digital gates. So it's going to be a 0-volt or 5-volt input. And remember that. And let's just think of either CMOS or TTL. That somewhere between sort of 3 and 5 volts is high, and somewhere between 0 and 1 volt is low. But between 1 and 2 volts is 1 and 3 volts is indeterminate. The other thing I'll note is that while we called our inputs A and B earlier, I never gave the output a name. We often call the output Q when we're talking about circuits. So we talk about A, B, and Q, input, input, output. So now imagine that we were to put 5 volts, or let's put 0 volts input on A and a 0-volt input on B. So 0, 0. And let's look at what the output is going to be. The output, right? There's no voltage anywhere. These are just diodes. They're not powered gates or anything. They're diodes. So the output is 0. There's no voltage anywhere in this circuit. So the output is 0. But now imagine that I put 5 volts on the input at A. So let's go ahead and put 5 volts at the input at A. 5 volts. So we're going to put 5 volts on A. That's a high. That's just 1. And let's keep 0 volts on B. That's a low or a 0. And just imagine what happens, right? So the diode gate, we're forward biasing the diode, so the current will pass through the diode, right? We're putting a 5-volt power supply there. And so the diode just has a 0.7 volt voltage drop. So this is 4.3 volts on that side of the diode. And it's 4.3 volts over a 1K resistor. So there's a 1K resistor there, so it's not shorted to ground. So this right here is 4.3 volts, and so the output is 4.3 volts. So that is considered high because, it's, again, CMOS or TTL, which this is neither, but it's within range of, let's just say high is 3 to 5 volts. We're just going to assume high is 3 to 5 volts and low is 0 to 1 volts approximately. Whoops. 0. Come on. 0 to 1 volts approximately. Okay. So that's still high, and the output's 1. And then you can imagine if I put 5 volts on B, right? What are we going to get? We have 4.3 volts. And if I put 5 volts on B, then we're going to have 4.3 volts on that side of B. And we have two 4.3 volt power supplies in parallel, which is just, I think it's just 4.3 volts. It's just 4.3 volts. And so, therefore, if A is high and B is high, then the output is still high, 4.3 volts on that side. And by the same argument, this is what you get. So you can see how that's the OR function. This is an OR diode gate. The output is going to be 4.3 volts unless both inputs are 0 volts. Of course, actually, one of the things that I was not careful about, which is maybe going to be more relevant for the AND gate, is when I had 0 volts on B, let me go back to 0 volts on B, right? That's, whoa, crumbs. Try again. That's this one here, 0 volts on B. When we had 0 volts on B, how do you put 0 volts on B? That is not an open circuit. That's a grounded circuit, right? Grounded circuit. Ground is where 0 volts is. 0 volts, right? 0 volts. That's where ground is. So to put 0 volts, you have to ground it. An open circuit is indeterminate. 0 volts is grounded. Okay. So for the AND gate, I said I wasn't going to do it, but what I want to point out is that if A and B are 5 volts, all right, I had to just think about it for a second whether I was going to tell you this answer, but let me just say it and then you can think about it. If A or B are 5 volts, if A and B are 5 volts, if A and B are 5 volts, then there's not going to be any current flowing in this circuit. If A and, so just think about that, right? Here we are powering this with 5 volts. This gate has a 5 volt power supply all the time. If A and B are 5 volts, there's not going to be any current flowing in this circuit. If A or B are grounded, if either one is grounded, then there's going to be current flowing through the circuit to whichever one is grounded, or both. And therefore, if this is 0, therefore that's going to be 0 volts, and this is going to be 0.7 volts. Whoops. And this side is going to be that's messy. And this side is going to be 0.7 volts, which is again in the range of low. So if either A or B are grounded, then it shorts to ground and you get 0.7 volts. If both A and B are 5 volts, then Q is just going to be 5 volts because no current will flow, so the voltage doesn't go down over the resistor. If you don't get that, think about it for a little bit. And make sure that truth table shows that it's an AND gate. So there's one other thing that maybe when you start thinking about these gates that you start wondering is what about the output? Doesn't the output change what the gate does? Yes, the output does. That's why outputs, we studied in a very early lab that the output ideally has an infinite resistance. So the output pulls ideally no current from the circuit. Because if the output was just shorted, then that would screw everything up here. That wouldn't allow these gates to work. So the output has an infinite impedance or a high impedance compared to the circuit, so it pulls no current, so we don't have to worry about current flowing to the output. So we don't have to worry about what the output's doing to the circuit. So what we're really doing with Q in either gate, Q is simply measuring the voltage at the point where that wire is attached, right? In the OR gate, the top one, right? Q is simply measuring the voltage right here, and the AND gate, the bottom one, Q is measuring the voltage right here. That's what we're doing. Is we're just measuring the voltage with a large impedance so that we're not affecting the circuit. And the other thing, let me just remind you of the fan out, right? Because for the OR gate, we've got that it goes to 4.3 volts, so the output now is 4.3 volts. If we then attach that to another OR gate, then the output of that OR gate is going to be 4.3 minus 0.7. It's going to be 3.6 volts, still high. But then we attach that to another OR gate, then it goes to 2.9 volts, which is now in our indeterminate, right in between level. And so the fan out here, you can figure out how many gates you can put in a row until the voltage is such that it is neither high nor low. Let me also note that the fan out here I'm talking about is putting gates in series, but what if you put the gates in parallel? A single gate in the lab, when you look on the fourth page of the lab, it shows the gates in parallel, a single gate driving a whole bunch of gates in parallel. The fan out in that case is the number of gates you can drive in parallel, which is a similar question. You can think about how many gates can you drive in that direction. So in the lab, on the next page from the one that I was just talking about, so I guess it's page 5, I guess if you're, I'm looking at it printed out. If you're looking at it on the computer screen, you probably can't tell, but then I ask you to build a gate with transistors. It's a slightly more complicated gate, and I know that, I know it works, and it works well. If you can't build it, rather than, you should struggle and you should try to build it, but in the end, if you can't get it to work on a circuit board, build it in Circuit Maker or whatever multi-sim you're using, and show that it works as a NAND gate. So I'm having you build one gate out of transistors, but then we're going to move on to actual IC gates, actual chips. So this is an image of the exclusive OR gate that I'm asking you to build. It's in the lab. This picture's in the lab. Whoops, except that I think it looks like there's one extra circle somewhere. Hold on. Okay, so the one thing I'm showing here, just to be sure we understand, is that where the two NOT gates, right, this is a NOT gate and this is a NOT gate, that the two NOT gates are not attached right there. Okay, let me delete that. The two NOT gates, those wires are not attached to each other. Okay, so there's no, oh gosh, I just want to make sure there's no junction there, right? No junction. Okay. So these are NOT gates, and these are NAND gates. So you notice there are 1, 2, 3, 4, 5 elements. There are 5 elements here. What I want to point out, though, is that when you get these chips, that when you the IC, the integrated circuit, the IC for the NAND gate, that there are 4 NAND gates on a chip. So this is a single chip, and you can there's 4 completely separate NAND gates. And I believe that that's the same thing with the inverter. Okay, let me try that again. So for the NAND gate, the chip that we're going to use, the 74LSOO, has 4 AND gates in it. I'm sorry, 4 NAND gates in it. It's got 4 NAND gates in it, and then the other 2 pins. So it's a 14-pin chip. So it's 14 pins, right? 2 NAND gates. 4 NAND gates. So there's 3 pins per NAND gate. So that's 12. And the other 2 chips are the power and ground. And you've got to power it with 5 volts, and you got to ground it, right? So the chip is powered with 5 volts, is grounded, and then you got 4 AND gates. We're only using 3 in this particular circuit, which for some reason I'm scribbling all over. And then for the inverters, called hex inverters, but the inverters, they're the NOT gates. The inverters are the NOT gates. They invert the answer, right? So an inverter is a NOT gate. For the 74LS04, which is the hex inverter, it's got 6 NOT gates on it. So look up the pinout. It's got 6 NOT gates. We only need 2 of them, so it's a single chip. And again, it's got power and ground. So you got to make sure to power it and ground it. VCC is the power, 5 volts. The ground is 0 volts, grounded. So this circuit is just 2 chips, 1 power supply, which you can use to power both chips, and a ground. So it's not so bad. And then it's just a bunch of wires connecting the pins in the right order. And then input, output. So then you need your signal input, and your signal input is either a 5 volt DC power supply, and your output is just measuring the voltage at the output, or we will talk about in lab using the pulsars and probes. They're just a simple way of putting in a high or a low and detecting a high or a low. But you can just use a 5 volt DC power supplies. Remember, all these gates, no AC. Nothing we're doing is AC right now. Everything is just DC power. It's either high or low. It's either 5 volts or 0 volts. The last part of the lab is a chip that has a neat function. I've always found it kind of neat and useful. It's called a multiplexer. The multiplexer, I think, is kind of cool. So the multiplexer we're going to use is an 8-input multiplexer. And you can have 8 different inputs, and then you simply give the multiplexer an address. You give it a digital address. You tell it which of the inputs you want to go to the output. So you can choose which input to go to the output. So I'm trying to think of an example. I'm sure you can think of examples of when this would be useful. But let's say that we were measuring let's say we were measuring the temperature in 8 different rooms in your house. And we had the temperature, and we wanted to just record those serially instead of in parallel, right? We just want to record them serially one after another. With some kind of device, whatever. So you could have the 8 temperature inputs going into the multiplexer. You have 1 output coming out, and that output is just gonna scroll through each of the inputs. So we're going to address each of the input, which they're going to say output number 1, now output number 2, now output number 3, now output number 4, and we can serially see what the temperature is, and we can just keep on scrolling through those 8. That's just an example. When I was in graduate school, we used multiplexers in order to choose, if we had a bunch of signals for whatever, it doesn't matter what kind of device, and just to choose one of those signals to go to look at for the output. I remember it was a pretty powerful little functional chip. So this is sort of an image of a multiplexer. On the left-hand side, we've got 8 inputs. So those are 0 through 7 are your 8 inputs. The 3, 0, 1, 2 on the right-hand side are how we address those inputs. So if we want input number 0, we're going to put in if we want input number 0 to go to the output, right? So all of these inputs can be connected to the output. If we want input 0 to be connected to the output, we're going to give an address of 0, 0, 0, right? So that's a digital address which equals 0, so that's going to connect the input 0 to the output. If I go ahead and I say, okay, let's address a different one. Let's say I want to have number 3 go to the output. Right? What would I have to do? I would have to address, we'd have to say 0, 1, 1, and now that's base 2, that's equal to 3, and so that says 3 goes to the output, right? Let me just do one more. Imagine that I wanted, I don't know, let's say number 6 going to the output, right? 6 going to the output. So how would I address that? Oops, wait a second. I made a mistake on the last one. Hold on a second. Because that was a mistake because 0, 1, 2, even though they're marked 0, 1, 2, it's the 1's place, right? The 1's place, the 2's place, and the 4's place, right? Whoops. This would be, so the input would be 1, 1, 0 to get pin 3 to go to the output. Okay, because that's the 1's place, 2's place, and 4's place. Okay, so now with that in mind, let's ask what we're going to do. Number 6, let's say we want 6 to go to the output. Let's see if you can figure out how we address number 6, right? It's just 6 base 2, right? So it's a 1 in the 4's place, a 1 in the 2's place, and a 0 in the 1's place. That's equal to 6, and so that's going to connect 6 to the output. So the 8-input multiplexer works like that. Grab yourself an 8-input multiplexer, hook up the circuit that I ask you to hook up, and see if you can show how it works. In the case of the lab, we're just going to have the output power an LED. Let's just rather than reading the output, we'll just have it power an LED. Go ahead and hook that up and see how it works. I will note that the very last one, the 31-day machine, is kind of a fun one. I do not ask you to build that or model that in Multisim. I'm just putting that in there. You can build it if you want, but it's just for fun. I will note that when you're programming computers, that you also come across, as well as decimal, right, 0 through 9, and binary, 0 and 1. We also come across octal, 0 through 8, and hexadecimal, 0 through 16. Right, so those come up to those bases, and in the same way that we were able to write numbers in base 10 or base 2, right, at base 8. In base 8, for example, the first digit is the 1s, the second digit is the 8s, the third digit is the 64s. 8 to the 0, 8 to the 1, 8 to the 2, 8 to the 3, etc. Hexadecimal, first digit, second digit, right? So this is 0 through 7. Base 10 is, of course, base 10 is 0 through 9. Base 2 is 0 through 1. Base 10, base 2, base 8, octal, hexadecimal, base 16. These come up, hex, but base 16 is 0 through 15, but we don't have, but it's got to be individual letters and numbers, so it's 0 through 9, and then A, B, C, A is 10, B is 11, C is 12, 13, 14, 15, right? So in base 16, A represents 10, B represents 11, C represents 12, and the digits are going to be 16 to the 0, 16 to the 1, 16 to the 2. We're not going to use this, but I'm just mentioning that these are often you come across these when you're doing various computer or sort of binary type things. So just thinking about bases, what is 1A hexadecimal number in decimal, right? So that's 1 is in the 16th place, so that's 16, and A is in the 1's place, and that's 10, so that's 16 plus 10, that's 26, right? So that's how hex works. Whoops, I wrote digital here when I meant decimal. Sorry. Decimal. So all that to say, I wanted to bring that up just in case you know a little bit about computers and you know that we don't always work in base 2 with computers. We usually work in powers of 2. Definitely powers of 2, right? Octal and hex is definitely 2 to the 3rd and 2 to the 4th. But all that was just so that I could tell you this joke. Why do mathematicians confuse Halloween with Christmas? Why do mathematicians confuse Halloween with Christmas? Because 31 oct equals 25 dec. 31 octal equals 25 decimal. Right? 31 octal. Did you get it? 31. So that's 3 times 8 plus 1 in octal equals 2 times 10 plus 5 decimal. 24, 25. Yeah. Ha ha ha. Okay, that's all I got. I don't think the lab's going to be so bad, honestly. And you got an extra week for... Oh, nope. You might be listening to this video for a different year. But anyway, the year I'm recording it, you got an extra week. So don't tell next year's lab. Okay, bye.